Hi all, in this tutorial video I will solve the problem which you can see on the screen. This problem has been put on my homepage already, and here I want to create an outline how to solve this problem. If you have already solved it, that's great. So here we see a beam which is placed in between two rigid walls, and this beam is loaded along its axis by a distributed force system P, and the length of this beam is L, and the cross section of this beam is changing. It's decreasing as coordinate X increases, and this cross section is decreasing such that the width and the height of the cross section decreases linearly, and it halves as X reaches the end of the beam. Okay, so we have A1 and A1 over 2 at the two ends, and B1 and B1 over 2 at the two ends for the width and height. And our goal is to compute A and B for a given P and L. So let's start the solution. So from statics, if we draw the free body diagram, we can write equilibrium equations for the unknown constraint forces. So this is the free body diagram, and we have to replace the constraints with unknown forces, so we have to put A and B at the two ends, and along the length we have this distributed force system P. Now from here we get one equilibrium equation, so the forces in direction X must give a sum of 0. So A plus B minus P times L must give 0. So the problem is that this is one equation and we have two unknowns, A and B. So we would need one more equation so that we can compute these two variables. And the equation will come from the elastic nature of this beam. We know that the overall elongation of the beam must be 0 because these two walls are rigid, they do not move. So the overall length of the beam cannot change, delta L is 0, and the overall length of the beam can be computed as integral 0 to L epsilon x dx, where epsilon x is the strain, and the strain comes from Hooke's law, which says that the stress can be computed as E, which is the Young modulus, times epsilon of x. We assume that E, which is the Young modulus, is constant for the whole beam. So the beam has one Young modulus. It doesn't change along the length. Now, epsilon can be expressed from here. And sigma x can be computed as the normal force function over the cross-section area of the beam. So the cross-section area is changing, obviously. It's decreasing in terms of x. And here I denote the cross-section area by A tilde because A is already occupied by one of the constraint forces. So let's see first how to compute the cross-section area, A tilde of x. So the cross-section area is the width A times the height B of the cross-section. A is decreasing linearly, and if we have x equals to 0, then it must be a1. So let's see. If this function, which I wrote, would describe a linearly decreasing function which has the value of a1 at x equals to 0 and the value of a1 over 2 at x equals to L, because as we see it on the figure, a1 over 2 is the width of the cross-section at B. Okay, so let's substitute x equals to 0. If we substitute x equals to 0, we have a1. If we substitute x equals to L, then we have a1 minus a1 plus a1 over 2. So we have a1 over 2. So this perfectly describes the nature of the width of this beam, or the beam's cross-section. Now let's see how to characterize the height of the cross-section of the beam the very same way. So we have to replace A with B, and then we have the proper function for the height of the cross-section of the beam. And we can also notice that A1 can be multiplied out from the first expression, so this is the very same as A1 times 1 minus x over 2L. This is B1 times 1 minus x over 2L. So the cross-section area in terms of x is A1 times B1 times 1 minus x over 2L squared. Okay, we have the cross-section area. Let's see how we can compute the normal force function. So let's draw the coordinate system in the free body diagram. And then we will use this sign rule to give the normal force function n of x. So n of x will be a minus p times x with this sign rule, so we go from the left. And then we can bring all the formulas together, so we can take this n and a tilde, put it into sigma, we can put sigma in epsilon, and then epsilon to delta L, and then delta L to this delta L equals to 0 equation. So I will write the final substitution. So we have integral 0 to L 1 over E times A minus Px over A1 B1 1 minus x over 2L squared dx. And this must be 0. So if we look at this equation, we see that A1 is unknown, P and L are known, and actually we can simplify with parameters E, A1 and B1 because those are constants, those can be brought in front of the integral, and then we can just simply multiply the whole equation with E1, A1, B1, and those will disappear from our equation. So finally we will have this integral. Okay, and we can just simplify it with this term. And this integral depends on L and P, and A is the only unknown, so A can be expressed from this equation, and then the value of A can be brought back to this equation, the equilibrium equation, and B can be expressed from there. So now comes the technical part. We have to carry out the integration of this expression. Let's see how to do it. So we have to integrate 0 to L A times 1 over 1 minus x over 2L squared dx minus P times 0 to L x over 1 minus x over 2L squared dx, and this will give us 0. Let's deal with the first part. So we cannot recognize any well-known primitive function for this expression under the integral. So our guess would be to make a substitution. So let's introduce a new variable for 1 minus x over 2L. And this will change our integral from 0 to L dx to an integral where x equals to 0 gives y equals to 1. So if we substitute 0 to x in this expression, we will get 1 for y. So we have to integrate from 1. And the upper bound is L, x equals to L. But if x equals to L, we have 1 minus 1 over 2 for y, which is 1 over 2. Okay. And then, instead of dx, we must write dx over dy times dy due to the substitution. So we have to compute dx over dy. We can do that if we express x from this upper equation. It will be 2L times 1 minus y. So from here we get dx over dy equals to minus 2L. So this will be minus 2L. Okay, and after this substitution, we finally will have minus integral 1 over 2 to 1, because we can change the bounds or switch the bounds if we use a minus 1 sign. 1 over y squared minus 2L dy. Okay, so this is simply 2L integral 1 over 2 to 1 y to the minus second power dy. Okay, and what's the primitive function of y to the minus second? It's minus y to the minus 1, because if we differentiate y minus 1 to the minus 1, we will have y to the minus 2. So we have to take this primitive function at 1 and 1 over 2, which is minus 1 minus 1 over 2, or 1 over 1 over 2. Okay, so this will be 2. So finally we will have 1 for this integral. Thus we have 2L for this integral, but we have to multiply it with a. So the first part of this equation will become a times 2L. Let's see the second part of this equation. So we need to integrate from 0 to L x over 1 minus x over 2L squared. dx. We will do the very same substitution. So again, we can reverse the bounds or switch the bounds, and we have to use this substitution for x. So for x we had 2l times 1 minus y, and here we had y to the second power, and instead of dx we had minus 2l dy. Okay, so here we see that this is actually 4l squared integral 1 over 2 to 1 over y squared minus 4l squared integral 1 over 2 to 1 over y dy. And we have already computed 1 over y squared, the integral of 1 over y squared, so this was 1. Now let's compute the integral of this expression. So the primitive function of 1 over y is the natural logarithm function. This is the primitive function. We have to take it at 1 and 1 over 2. So we will have natural logarithm 1 minus natural logarithm 1 over 2. And there is an identity which you should know from high school. So that identity says that ln of x minus ln of y is ln of x over y. Okay, we can apply this identity, and then we will have natural logarithm 2 for this part. So the final result, what we had for this integral, is 4l squared 1 minus natural logarithm 2. Okay, we can bring this back to our original equation, and then we have an equation for a. So this is 4l squared times p times 1 minus natural logarithm 2. So we got an equation for a. That equation is a times 2l minus 4pl squared 1 minus natural logarithm 2. This is 0. We can express a from this equation. A is equal to 2pl times 1 minus natural logarithm 2. So we have an expression for a, and we can bring this back to our equilibrium equation, which was a plus b minus pl is 0. So from here b is equal to pl minus a, which will give pl minus 1 plus 2 times natural logarithm 2. And this is actually natural logarithm 2 squared. So the final result is pl natural logarithm 4 minus 1. Okay, so here are our final results. Hope you enjoyed this video. Thanks for watching it. Hope it was useful. If you have any questions, don't hesitate to contact me either personally or through email. See you at the next tutorial.